All right. Happy Labor Day, everybody. We're going to just have like a little short little bit here where I'm going to talk about the other three factors that we're considering when looking at the acidity of organic molecules. And so that's as far as we're going to go today. So, just depending on how long it takes us, maybe it'll be half an hour, maybe 45 minutes. We'll see. Maybe less. We'll find out. And then by then I think we'll be all caught up where we need to be, and then we can finish the rest of kind of this idea about acids and bases on Wednesday. So hard to keep the days in track, right? So, what we've talked about in terms of factors that contribute to a particular compound's acidity in terms of organic compounds, we first looked at the case of having a protonated substance versus its non-protonated counterpart. And of course, the protonated form is going to be more acidic, right? We saw that it's going to have a more stable conjugate base once it reacts. Good morning. Oh my god, my allergies are just killing me today. Sorry. You'd think September by now they'd be over, but no. The second case we looked at was the identity of the atom to which your hydrogen is attached. And we saw that the bigger the size of your atom, the more polarizable it was. It can accommodate the negative charge more readily. And so we saw that bigger atoms are better at kind of holding a negative charge, and so they're going to make better acids as a result. And that size factor is going to be more important than electronegativity is. So if things are relatively the same size, then you'll look at electronegativity. So for example, we're going to see if we compare similar compounds here. Whatever, I'll put one of those as the acidic one. When we're comparing those two, we see that in this case the electronegativity is going to be the winner here because they're in the same period as each other. And in the case of the above example, we saw that the sulfur is much, much larger than the oxygen, and that's the more important factor when considering the acidity of the methyl sulfide there. So those are the two we're looking at. So here this is about electronegativity because of the same period. And here it's about the size. That's why the sulfur one will be a stronger acid. Alrighty, so we've covered those two. We've got 3 to go. The next one, these are somewhat hierarchical. So in most cases, these factors are going to be most important being, the comparison between a cationic and a non-cationic acid. Then after that, we look at the identity of the atom to which is attached. And then after that, now we're going to look at resonance. Yet again. So, just a refresher on this resonance idea. Remember that these are pi electrons, or rather just kind of pi electrons or delocalized lone pairs that move around within a molecule. And remember, we had some rules with those. So remember, we're always starting resonance from a lone pair or a double bond. So pi electrons or delocalized lone pairs. Those are places where we can start resonance and we end it in essentially the same spot. So either forming a new double bond or forming a new lone pair on an atom. Those are places where we can end our resonance. We saw that for something to be more stabilized, we saw to minimize formal charges. We saw if things were negative, we would give them to more electronegative atoms. We would also if it has to be on carbon, we would put it on a primary carbon. Although we'll see later we have better types of carbon to put it on than a primary sp3 carbon. And then if we have cations in our structure, we saw that, so what I had kind of neglected is, first thing, you do want to make sure everything has a complete octet, if possible. So if you're going to be dealing with positive charges. So positive charges on things like oxygen, nitrogen, sulfur, those are generally okay because they don't have incomplete octets, but carbon will have an incomplete octet if you have a positive charge in it. So we want to avoid those as well. But after that, after you've made sure your octets are okay or you can't do anything about it, then you'll want to see if you can put your positive charges onto less electronegative atoms, like nitrogen would be a better choice than oxygen, for example. And then if you have to have it on a carbon, you want it to be in a tertiary position where you can have hyperconjugation stabilize it. So that's a quick little recap verbally of our resonance rules. Hopefully you've been practicing them on some of the molecules on your homework. I do suggest also there's plenty of book problems, both at the end of the chapter as well as kind of integrated throughout. Those are excellent problems to work on to practice your skills. So, resonance now. We're going to see that, just a kind of short bit here, that resonance can greatly stabilize negative charges. For example, if we're looking at comparing these two hydrogens, a carboxylic acid versus an alcohol, well, hopefully one of them, since it has the word acid in its name, should tell you it's going to be more acidic. But we're going to see here that the pKa for this one is around 5, and here around 15. So we have a 10 to the 10 difference. That is 10 billion times more acidic, the one on the left there. And so the reason for that is because of resonance. If we look at these, neither of them are cationic, so we can skip that. They're both on oxygen, so we don't have any atom differences there. But now we're going to see that one of them can resonate and the other cannot. So if we take a look at the conjugate bases, we remove those hydrogens. We're going to see, this one can essentially shift its negative charge to the other oxygen. If we do that, now we see we've kind of moved that lone pair, that negative charge, over to a different oxygen. And so as a result, we kind of have this idea that we have this kind of negative charge spread between them. Like if we kind of combine those two, we see that, we actually have that lone pair kind of still hanging around somewhere in between the two. So it's not localized at any one of those particular spots. And so by delocalizing it, so it's delocalized, participating in resonance. So we're going to see that this one's going to be a lot more stable. This carboxylic acid is going to be more stable than our alcohol here, plain old alcohol. So again, 10 to the 10 difference here because of resonance. So we're going to see, because one of these could resonate that lone pair away after you remove the hydrogen, you get an extra lone pair, right? And so as a result, that stabilizes the negative charge quite a bit, and so it can accommodate that more readily, and we're going to end up getting good things out of it. So we're going to have a stronger acid because that acid can resonate. Its conjugate base can resonate. Remember, at all of these, we're really looking at the conjugate base and comparing those, because that's going to determine what the acidity is going to be. All right. If we see another example, sorry, we'll do this. Comparing these two, again, I'll put our acidic hydrogen here in light blue. Oh, this is jumping around. Both of these molecules can resonate once if they take them off. There's Oz with his sneezing again. Let's go ahead and take a look at their conjugate bases. So remember, conjugate base, we're going to essentially just replace that hydrogen with a lone pair. Poof. Oh. We've actually lost our oxygen too. That's not good. Okay. So, both of these can resonate, right? There are other pi electrons that we can mess with in both of these molecules. So we can go ahead and dump that in and move things around. Again, this one is going to have multiple resonance forms, because you can choose to, instead of pushing these double bonds around, we could choose to end on any of these carbons, essentially. But let's just compare. And if we take a look at this one again, we can see what we get by resonating these. If we resonate the one on the left, we end up with a lone pair on that carbon, and the negative charge there. And just like before, I really should remember my lone pairs everywhere. We end up with the lone pair on oxygen in this other one. And so, remembering our rules, this is a better... by resonating that lone pair onto another oxygen, an electronegative atom, that's going to be better than resonating it onto a carbon, right? Because carbon is less electronegative. Yes, exactly. Kevin's got it right there. So, definitely, that having it resonate onto a second oxygen is going to be better than resonating it onto a carbon. So, this resonates onto oxygen. This one resonates. Oops. Just remember, we could choose really any of these carbons to resonate that lone pair onto, but even having all those different carbons to resonate onto still is no match for the being able to resonate onto another oxygen. And so we're going to see here that the pKa's, if I scroll up, sorry, again, it's so hard to compare molecules because I only have so much space, right? This one, again, we're looking at a pKa of around 5. Here we're looking at around 10 or so. Even though this one can resonate, it's going to be a lot better than the alcohol, right? There is resonance here. But the resonance for the carboxylic acid is indeed better because it's resonating that lone pair onto an oxygen rather than onto a carbon. And so as a result, we're going to end up with a better option there. So therefore, because that right set of molecules is more stable, the conjugate bases are more stable, that's going to come from the stronger acid. So the acetic acid there is going to be stronger acid than phenol is. All right, so that's kind of how resonance can fit into all this stuff. All right. we can do some comparisons as well. This one I like. It's from the book. Oops. Comparing these two hydrogens. So, if I'm asking you to compare, okay, which of these two hydrogens is going to be more acidic than the other? What we want to do in each case is take a look at the conjugate bases. So, if we remove the green one, the best part about all this stuff is I can just clone all these while you guys have to draw them out. Well, I mean, maybe not, depending on what you're using, but let's compare these. Actually, I'm going to put them in the same row just so we can compare them like kind of side by side. So let me erase the other one. Okay, so if I remove the green one and the blue one, don't forget nitrogen is already going to have a lone pair by itself. Okay. Alright, finally, I've drawn our conjugate bases. So, I mean, Kevin, you're right, there is induction here, but resonance is going to definitely outweigh induction every single time. So, but we'll take a look. So, blue one. So both of these are, neither is cationic. So they're also located both on nitrogens. Indeed. We'll talk about, well, I say cario, but ario works, yes. So neither of them are cations. They're the same atom. And now we're going to look at resonance. We're going to see that this blue one here cannot resonate. The reason for that, there are no pi electrons nearby it. There are no, it's only got single bonds around. If it tries to go ahead and plop onto this to make a double bond, we're going to end up having 5 bonds to a carbon, and that is a big no-no. So, can't do it. No resonance for the blue one. But, indeed, we can resonate the green one, because there is a pi system right next to it. So, on the adjacent carbon, there is a double bond, which means we can resonate there. And so, as a result, we have resonance onto an oxygen. And in fact, you probably will end up with the following. This is probably actually a better structure than our original molecule was, right? Because now we have the negative charge on the oxygen rather than the nitrogen. So we're going to see that, in fact, it's probably going to favor that bottom one anyway. So that's going to be the better one there. So in this case, we end up going to resonance. And so resonance there is going to be the factor in determining that the green proton was the more acidic one in this molecule. All right, so it's all a matter of comparison. So the first kind of step within looking at resonance is, can both resonate? Sometimes, in this case, only one of them could resonate, so by default that one's going to win, because only one could. But if both can, if we were to change this around, if we're comparing these, if we're comparing these, if we get rid of the blue one and the green one, it's going to kind of do them the same way. We're going to see the green one can resonate to an oxygen. The blue one can resonate to a nitrogen. So while now both can resonate, the green one's going to resonate onto an oxygen. Blue one's going to resonate onto a nitrogen. Oxygen's more electronegative. That resonance form is going to be more stable than the other one. So the oxygen one is going to win here. So the green one will again be the winner. So it'll be more acidic. Or we can say it'll have a lower pKa. Remember, pKa is inverted with acid strength, so low pKa means higher acidity. I think we didn't say it here, but this is the winner here, being more acidic. Okay, so any questions on this set of molecules or this bottom one down here? Hopefully, again, we're going to see how the resonance makes the green one better in this case as well. All right. So that's resonance. Next one we have is induction, as Kevin has pointed out. Whoops. This is number 4. In deduction. Okay, let's try that again. Induction. There we go. Induction. So, briefly, I think last time I had mentioned this a little bit. I might have used a fluorine. Why not? We can use a fluorine. So I'm going to explicitly draw a hydrogen there just so we see that's the difference between these two. So if we look at these, difference between fluorine and hydrogen, of course, is a very large difference in electronegativity. Let's look up some numbers here. So we already know that the pKa of this carboxylic acid is around 5. I think for acetic acid is 4.75, but around 5 is fine. Let's see. Let's look at the pKa of this. Fluoroacetic. There we go. Fluoroacetic acid has a pKa of 2.5. Okay, so putting the pKa's there so we can all see those. We're going to see, yes, having an electronegative atom nearby is going to make things a little bit more stable through the process of induction. The reason being that fluorine, remember, is going to be pulling electron density towards itself. As a result, making this carbon a little bit positive and the fluorine a little negative, right? It's a polar bond. Carbon-fluorine bond is polar. As a result, when we go ahead and pop off these guys and resonate them, let's just do this all at once. When we resonate these, and we end up kind of sharing the negative charge between those oxygens, we now have a negative charge kind of moving in between those two through resonance. Aha, but now we have one of them that's got a nearby partial positive. And as a result, there's kind of this chain effect happening. So, of course, we like positive and negative to be closer together, right? But like a little bit, we're going to have a smaller dipole there. Like that carbon, when attached to the fluorine, is going to be pulling electron density away from the one with the oxygens. And so we're going to help stabilize this. So this stabilizes the negative charge by providing a nearby partial positive. That's a really ugly nearby. Nobody could read that. There we go. So do we see how that happens? So again, we're introducing a slightly positive charge into our molecule, and that's going to help balance out the negative charge that's right next to it. All right. Any questions on that? We're going to look at some more in just a second. So that fluorine there, able to withdraw electron density, pulls it towards itself, helps, again, spread out the negative charge there. Helps pull stuff towards itself, so it's going to help balance things out. So we're going to see that this inductive effect kind of, it decreases with distance. So if we are comparing we'll even make these propionic acids now. We're going to see, well, both of these have the fluorine pulling electron density towards itself. But we're going to see this one is closer again, I'm drawing the acid form, but I really should be drawing the base because we are always comparing the base. Let's redraw these. And I'm not going to draw it resonated this time because why not? I can do it either way. We're going to see here we have that positive charge, partial positive, is closer to the negative charge on the oxygen in the left molecule. In the right molecule, we have the fluorine is a little bit farther away. It's one carbon farther. And so as a result, we're going to have... I should continue the same color. We're going to see that the left one is going to experience the greater inductive effect. And therefore, this is going to be more stable than the one on the right. Again, the one on the right is still better than not having it at all, for sure. But it's going to be a little bit less. Let's see if I can... I wonder if we've got these. So, 3-fluoropropionic acid. Oh, let's Google it. Let's see. Propionic acid pKa. Okay. Did we get a pKa here? Come on, pKa. I'm not seeing one pop up here, but I don't have the numbers for you, unfortunately, with this particular one. But suffice to say, it's still going to be better than having... it's going to be better if it's closer. And as you can see here, the positive charge is closer to the negative. Of course, it's going to be more stabilizing, right? So, a little bit intuitive there. Another comparison we can make. which of these do we think is going to be better? Which one's going to have the stronger inductive effect? So again, we're looking at these. They're not cationic. They're both on oxygen. They both can resonate the same way. So now we're looking at induction. Otherwise, they're identical molecules, right? So we're looking at these things kind of in order. Indeed. So Kevin has got the right idea. So the fluorine being more electronegative, it's going to have a stronger dipole. Which means that we have a greater partial positive on carbon, therefore more induction, therefore more stable. So we have quite a lot of reasoning to go through, right? So thinking about things we've learned in the past, fluorine is more electronegative than chlorine, therefore it's going to create a stronger dipole because it's going to pull more electron density away, therefore giving a greater positive charge on the carbon next to it, which is therefore going to stabilize the negative charge in the conjugate base to a greater extent. Therefore, the acid on the left is stronger because its conjugate base is more stable. So, we're going to see here again, this is going to be the stronger acid. I didn't do that here, but stronger acid again on the left. All right. Induction can also kind of work against us as well. We have a minor effect here. But it's still useful to talk about. We're going to see okay, if we compare these two, we're not really going to have induction per se, because a carbon-carbon bond and a carbon-hydrogen bond, roughly the same. I mean, we don't consider either of those to be polar, right? But we remember perhaps earlier, like if we were to put a positive charge, what was for the last question? Stronger inductive effect? Yeah, that was I knew that was for the last question. Yeah. No worries there. We're going to see that the pKa of this 4.75, 4.76, whatever. This one's about 4.88. Little bit stranger. Right? Very minor difference. Yes, indeed the answer is hyperconjugation. So remember, hyperconjugation stabilizes positive charges by allowing them to kind of have some orbital overlap as things are moving around. It's going to actually destabilize negative charges. And that's why, again, we want our negative charges to be on primary carbons, right? We're going to see that having just this extra carbon here bumps up or bumps down our acidity a little bit. We're very slightly less acidic. It's like maybe 1 versus 1.5 or something. It's a small difference, but still is noticeable. So there's no B in this. Hyperconjugation stabilizing, or rather, which stabilizes it will destabilize because it's essentially adding in electron density. The inductive effect we saw before with the halogens, it's withdrawing electron density. And so we're going to see, we can, we're able to have that partial positive there, and so things are going to be nice and happy. This is actually going to create a very, very small negative charge. I mean, it's not even really. As you can see, the difference is quite minor here. But just that kind of small extra electron density from the carbon next to it, that's going to destabilize it just a little bit. And so we're going to end up with a higher pKa. We're going to see that this is going to be the stronger acid in this case. So because there are fewer carbons to throw in some hyperconjugation here. So slightly. Let's see if... What's the name of that acid? It's the tert-butyl acid. Here, I'll do this. This will be 1,2,2,2-dimethylpropanoic acid pKa. Let's see if we can get this one. Let's see if we get a pKa out of this. pKa, where are you hiding? 5.03. So if you if we have one that is got now methyls everywhere, carbons everywhere, that is to say. Shouldn't do it that way. Okay. This one's got a pKa of 5.03. So again, more carbons we throw in here, the more hyperconjugation we have. Hyperconjugation destabilizes negative charges. So we're going to see that the more carbons we kind of throw on next to our negative charge, that's going to end up destabilizing it just a little bit. But it's kind of the same idea. So we'll just put that with induction. These are very minor, though. You saw just with regular induction, it was a difference of 2 pKa units, right? So that's 100 times more acidic, the one on the left. 100 times more acidic. These, it's like 1.5 times more acidic or something. It's minor. Very minor. But still there. All right. How's that one looking? That one's okay? Hopefully. All right. Then the last one we have, we're dealing with the orbitals now. We're going to see I shouldn't do that. Okay. So this is the hydrogen on the sp3 carbon. We're going to see the pKa's here. We see what's called a vinyl hydrogen versus an aliphatic hydrogen. These are words that we use to describe these. What's the word for the acetylene one? I don't know if there's a word for this. SP, we'll say for now. I don't think there's a word for this particular one. Anyways, when we're looking at these hydrogens, we're going to see the orbital to the carbon to which it's attached makes a difference. I mean, just looking at these numbers here, we see a huge difference between the sp3 hybridized carbon, the sp2 hybridized carbon, and the sp hybridized carbon. And for this, it helps us to kind of revisit hybridization just a little bit again. If we take a look at these orbitals, if we want to just kind of think about what these mean, this means that this orbital is 25% s, 75% p, if it's sp3. If it's sp2, we're looking at about 33% s and 67% p. And then for sp, we're looking at 50-50. Remembering that s orbitals are spherical, p orbitals are this kind of dumbbell shape. If we want to look at the hybrid orbitals, exaggerating a bit here, but the more p character we have, we see these orbitals get longer and longer, because the p orbitals are vertically kind of more, distended than the s orbitals, which are spherical. So we're going to see that the more p character we have, it's a longer orbital, and it's farther from the nucleus. Or rather, there are regions of it that are farther from the nucleus, like its range is farther. And so we're going to see here that if we're going to put a pair of electrons into each of these orbitals, we're going to see, well, this sp1 has this negative charge closer to the nucleus. Nucleus, as we know, is positively charged. So, having an sp carbon, which has more s character, it's more spherical, it's kind of a shorter orbital, is going to be a little bit closer to the nucleus. Those electrons are going to be kind of hanging around closer to the nucleus, and so it's going to stabilize that a little bit more. Actually, a lot more. But we'll also see there's some geometry going on here that's going to be important. And then if we look at the sp3, the other extreme of this, we're going to see electrons can spend more time farther away from the nucleus, and so there's going to be less stabilized by the positive charge of the nucleus, and so as a result, we're going to see that's going to have a little bit less stability there. So we're going to see more stable, less stable. But if we look at geometry, again, I'm going to just focus on the extremes. The sp2s are in the middle. We know this angle is 180 degrees. This angle here is 109.5, right? And we remember that, with nitrogen, for example, when we put a lone pair on, we ended up pushing our angles just a little bit. 107.9 or so. Those are actually going to be in between the hydrogens. So we're actually going to have a larger, if the difference is, we've subtracted one from the other side, maybe this will be about 111 degrees or so. Something like that. Between the lone pair and the hydrogen versus the hydrogen-hydrogen bond angle there. So, remembering that electron domains they repel each other, right? Because they're essentially negative charges. They're just electrons hanging around each other. We saw that if we're actually going to have this, with ammonia, we're going to see those bond angles, but we're going to actually see that the a negatively charged lone pair is going to be just kind of slightly more obtrusive than a regular lone pair would be. Because, that carbon can't quite contain that extra negative as well as some of the other atoms can. So, because it's not terribly electronegative. So, we're going to see that if this orbital that contains the electrons is going to be obtrusive, the one on the sp hybridized carbon has got plenty of room. It's already 180 degrees apart from its next electron domain. So it's already kind of got its maximum repulsion. So it's kind of got plenty of space to hang out, as it were. Got plenty of space on this side. There's no other electron domains repelling it, so it's kind of happy. This one, though, has got all sorts of stuff nearby. It's got bonking that way, that way, that way. We've got all sorts of unfavorable things that could happen nearby this lone pair. And so it's kind of got less space. Again, I'm kind of framing it in this idea of, that they want to spread out and have lots of space. It's, again, really a repelling thing. So what I mean by plenty of space is that there's less repulsion. So kind of just framing it in a way that's maybe a little bit more intuitive. Electrons want more space, right? And so if they can have more space, they're going to be more stabilized. But really what I mean here is that there's less repulsion between domains here. So we don't have a lot of stuff in the way of our sp hybridized carbon bearing the lone pair versus we do on an sp3 carbon. So again, with the middle case, we're going to have that 120 degrees. Might be like 124 or so, a little bit higher because the lone pair does push things a little bit farther. But we can see here, I'll write it out. I'm going to get rid of our lovely tetrahedral one. That's going bye-bye because that's not really relevant when we're talking about lone pairs. There are no lone pairs. If we're looking at these bond angles, we're looking somewhere here just a little bit less than 120. Or this one this will be kind of just a little bit more than 120. Just a little bit. 122 maybe, whatever. We see here, let's say it's 111 and 121 or something. Those two are fairly close to each other, right? Those bond angles compared with the 180. We see that 180 is a lot bigger than 120, which is bigger than 110 or 111 or whatever. Here, we'll even say 121. I don't quite know the exact angle, but we see this is the case. So we see that these two are more similar. We also saw that the pKa corresponding with these geometries, with these angles, we see again the same pattern here. So that's kind of the relationship we're looking at. So there is the effect that the sp hybridized orbitals are more spherical, they're more s character than p character, or they're equivalent s and p, right? And so we're going to see those are held closer to the nucleus, and they have kind of more room to, not repel with things. And so as a result, those are going to be our stronger acids. And on the other side of things, we have kind of longer, more p character bonds that are going to end up bumping into things more often. And so as a result, those are going to be less stable, and therefore they're going to come from weaker acids. So that's the idea of the orbitals here. The more S character you have, here's kind of the summary here. The more S character the orbital has, better it can stabilize a negative charge. And therefore, we're going to see that our sp hybridized carbons are going to actually have relatively stronger acids compared to the sp2 or sp3. And in fact, if we take a look at these two, for example, we'll see that this is actually a pretty strong effect. Although typically, again, we're going to look in the order of cations, then we're going to look at atoms, then resonance, then induction, and then orbitals. You might be tempted to say, okay, well, look, nitrogen's better to hold a negative charge than the carbon is, and you're correct. You're not wrong there. But we're going to see in this case, the orbitals are actually more important. So we're going to see the pKa here. Quite a big difference, even though the other ones are on nitrogen. So in fact, if we were to put, well, this is a sample of things to come. We're essentially going to see no reaction going this way. We're looking at a difference of 10 to the 10, right? But if we were to do this, why do I have a star? Oh, there it goes. No. What is happening here? Okay. There we go. We're going to see this one will deprotonate the other one. So we're going to talk about this later in terms of equilibrium, but we're going to see the K for this, the K, Kc, Keq, whatever you want to call it, is about 10 to the 10. So really not an equilibrium at all. But we're going to see there are implications for all of these things that we're going to learn when we talk about pKa values. So that's just a kind of look forward of what's to come in the next class here. So right now, though, those are all the factors. Sorry, these are the factors that we're talking about. So we're looking at cations, if things are cationic or not, or protonated. Then we're looking at the identity of the atom to which your hydrogen is attached. Then we're looking at resonance. Then we're looking at induction, and finally we're looking at orbitals. Those are generally done in that order. However, here's a very common exception. We see that indeed the nitrogen should win in point 2, the identity of the atom, but in fact, reality shows that in this particular comparison, it's the orbitals that matter more. So, rule of thumb, follow them hierarchically, but know, as always in chemistry, there are exceptions. And sometimes those exceptions are very important. Synthetically speaking, this is a very useful reaction, this bottom reaction here. Very, very useful. We're going to see to make things, to make carbon-carbon bonds is not very easy to do. Having this substance here, the acetylide ion, This is very useful for synthesis. So very, very important reaction, and we're looking at an acid-base reaction here, right? We're looking at a hydrogen moving from one substance to another. It's sort of the Bronsted-Lowry type of acid-base reaction. Anyways, let's just kind of summarize this now. What was the second one? Atom identity, resonance, induction, and then orbital type. These are the 5 factors. I think our book only covers 4, but that's okay. So as Kevin mentioned, there's this REO idea. The cation one's super easy. Again, we're saying, is this going to be a better acid than this? You better believe it. That's the cation one, remember? So we're going to see that that's definitely a factor. So, but looking at these, when we are, in your homework, unless you're given pKa's, when we're looking at these, you'll follow this order. So you'll first look at where the kind of first point of difference is between the molecules you're comparing. You might be saying, okay, well, neither of them are cationic. That's out the window. Are they attached to the same atom? Is one of them on a sulfur, the other is on an oxygen? Sulfur is going to win. Is one on an iodine, one on a fluorine? Iodine's going to win. One on a nitrogen, one on a carbon? Nitrogen's going to win. So, important things there. Then, resonance. Can it resonate? Can one resonate and not the other? Or can both resonate and one has better resonance? That's what we're looking at there. For induction, we're looking at, do we have an electron withdrawing atom, like a halogen, nearby, that's pulling electron density away? If we have one, if we're comparing, if both of them have electronegative atoms, which one is more electronegative? Are they equally distant from your point of negative charge? That's what we're looking there. And then finally, the orbital type. What type of orbital is our negative charge going to be put onto? We saw that again. sp is the best, then sp2, then sp3. All right. So that's all of our acid stuff. Took about an hour today, which is good. We're pretty much caught up. We're where I want to be in terms of progress this semester, so we're looking good. I know on your homework, I did include the idea of nucleophile and electrophile. I'm going to just very quickly throw this out there because I realize it is on the homework. The homework is from a previous semester where I would have taught these terms sooner. I wasn't planning to, but since I did not change your homework, I'll have to do that. So, these are terms we're going to formally define later on. But for purposes of our homework, I'll just kind of explain them to you. So, things that make a good nucleophile that we're going to call something a nucleophile, we want a localized negative charge, if possible. So something like this guy is going to be, hey, we have a visitor, more likely a nucleophile. He's up here probably being naughty. This one's AJ. If you might remember, one of the one-eyed ones is up here looking for treats. We're going to see that something with a localized negative charge, we're going to more likely call a nucleophile. it's going to attack a nucleus later. We'll see how that works in a few chapters. So we're going to, again, hold off on formally defining these. We're looking at, if not, we're looking at lone pairs on electronegative atoms. Those are kind of our other kind of ways we can get nucleophiles. And then also we're also seeing factors that destabilize negative charges. For example, never mind, let's not use that example. Let's use this. If we're looking at these carbons, for example, they both have localized negative charges, but we know that the one on the outside, the primary carbon, is a little bit more stable. So we're going to see that things that make it less stable, because it's secondary, that means it's more reactive, and we will call that a stronger nucleophile. So if we want something to be a good nucleophile, we're looking at kind of the opposite of all that stuff we talked about, stabilizing the conjugate bases. For things to be good nucleophiles, we want them unstable. We want things to not be very happy where they are, because therefore they're going to be reactive. And so we're going to say nucleophiles are essentially unstabilized negative charges. That's what we're looking for there. And guess what? Electrophiles are exactly the opposite. Electrophile is a little bit of an easier term to understand. We know electron. Phile means loving. These things want electrons. We're looking at localized positive charges here. We're looking at partial positive charges as well. So, for example, this guy here is an electrophile. That carbon right there is an electrophile. Technically, the oxygen could be a nucleophile. It's not a very good one because it doesn't really have a negative charge, but it has a partial negative charge. A full positive is going to be a better electrophile. Partial positive could be as well. And now we're looking at things that destabilize positive charges. So, for example, if you've got a tertiary carbocation versus a primary one, remember that primary ones are much less stable than tertiary ones. So if something is... Electrophiles get attacked by nucleophiles. So the more unstable your electrophile is, the more likely it is to be attacked. And so, again, here, let's look at our examples. If we have these, we're going to say this one's less stable. Although we will find out that they are so unstable that, in fact, your carbocation will just move by itself without even being attacked. Later on, we'll talk about that, but these are just kind of general trends. More reactive, and we would call this more electrophilic. But for now, I know there's just that kind of last question on your homework that asks about kind of electrophiles and nucleophiles. So these should hopefully make it pretty clear when we're talking about those. So if it has none of these things, if it's just a plain old carbon, then it's neither an electrophile or nucleophile, or it could be both. But let's not worry about that for now. So on that one, hopefully you'll be able to identify one of those should be obviously an electrophile, one of them should be obviously a nucleophile. And then for the others, you can write neither. So, cool. he's all squirmy. You want to say bye-bye to everybody? Bye-bye. Happy Labor Day. Yes. So, the better you can stabilize your conjugate base by whatever means possible, that's going to make your acid stronger. So, we can't really compare acid strength directly by looking at the acids themselves. We always want to look at the conjugate base. The conjugate base determines everything. So, I'll write it in purple because why not? Stop squirming, dude. Here, I'll put you down. Okay. The more stable conjugate base arises from the stronger acid. So, those 5 factors we talked about all contribute to the stability of the conjugate base. So, absolutely, if something can resonate and the other can't, and otherwise they're all the same, then the one that resonates will come from the stronger acid. Absolutely. So, this is the big picture here. So, if nothing else, if you're able to deduce this, that's what we're looking for here. This is the main point. Okay, cool. Alrighty. As I said, we'll end a little bit early today because why not? It's a holiday. So, thank you for those of you who were able to come today. That's awesome. And then the rest of you can just watch this later. So, great. Alright, we'll continue on Wednesday. We'll finish the rest of the chapter. We're on chapter 3, which talks about acids and bases. And maybe we'll start a little bit into alkanes on Wednesday as well. So we'll see. Okie dokie. Take care, everybody. Enjoy the rest of your holiday.